an s orbital. No orbital can handle more than 2 electrons. That's the most that can go into an orbital. It's sort of like saying the room's occupancy limit is 2 people. Okay? I don't care whether it's a big room that you've rented out or a broom closet. The most that can fit into that room, the most that can fit into any orbital of any kind, is 2 people, 2 electrons. Now, in order to have a stable arrangement, electrons repel each other, don't they? Yes? Okay. And because they're negatively charged. If they're spinning, they're going to be spinning in such a way to act as a magnet, right? Now, you know, you've played with magnets before. You can situate the magnets so they repel each other, right? Or you can situate them so they attract, which is supposed a more stable arrangement. Attract. So in other words, the electrons already are at each other's throats. They're already repelling one another. If we can minimize that, one way of minimizing would be so that they're at least a little bit attracted because of their magnetic fields. They're still going to be repulsed overall. But we can minimize that repulsion. The way to do that is to make certain that we don't have 2 north poles together, okay, or 2 south poles. In other words, we need them to have opposite spins. And so, 2 electrons belonging to the same orbital will naturally have opposite spins. It's just a more stable arrangement because it minimizes repulsion. The first electron to go into an orbital, so this is the convention I was talking about. The first electron to go into the orbital is assigned the m sub s value of -1/2. Okay? The convention is we always fill negatives to positives. So for instance, if I were going to put an electron into the second energy level, the second sublevel, p sublevel, these 3p orbitals all have the same energy. So does it matter which one I put it in? Well, technically no. But by convention, we just simply we start putting them in negative first. So we put it in this one first. You guys understand? If you go ahead and put an electron in, the first electron to go into that orbital gets the m sub s value of -1/2. The second electron to go into that same orbital would get an m sub s value of +1/2, indicating it's spinning in the opposite direction, and therefore it's a more stable arrangement because it minimizes repulsion. Questions? No questions? All right. Well, I need to point something out to you. You know how as we go out, the energy levels get closer and closer together? You know how the number of energy level, sublevels that make up the energy level get more and more? Well, they start to overlap. So it turns out that the 4th energy level, the 4th building, its 4s sublevel is actually right here. The 4s is actually lower in energy, overall closer to the nucleus than the 3d. Now, a fourth energy level electron, on average, I mean, if you're going to bet money, you're going to bet, yeah, 4th energy level electron has more energy than a 3rd energy level electron. But the 4s is actually lower in energy than the 3d is. Well, then what amount of overlap you get? Well, after the 4s is the 3d, and then you have, after the 3d, then you have the 4p, but then you have the 5s, the 4d, the 5p, the 6s, the 4f, the 5d, the 6p. Yeah, it gets a bit involved. So how do you keep track of where all those overlaps are? Glad you asked. We have a nice little way of dealing with it. And if you flip over to page 14, you can see what is called the diagonal rule. The diagonal rule at the bottom of page 14 is a nice, easy way. You have to be able to construct this so you can see what order to fill them in. And the way to do this is just to do it in an orderly fashion. So this is 1s, this is 2s, 2p. So this is the second energy level with its two sublevels. Notice I'm keeping my s's nice lined up. So this is the 3s. I put my 3p right underneath. I'm just trying to be neat here. Then the 3d. Then the 4s, the 4p, the 4d, and the 4f. Then it's the 5s, the 5p, the 5d, the 5f, Now, technically, there's a 5G, but here's the thing, guys. We never find electrons in the 5G sublevel when the atom is in its lowest energy state. Well, does the 5G exist? Yeah, it's like the 22nd floor exists. Just because there's a 22nd floor on a building doesn't mean someone's there. Okay, you can have a floor with nobody on it. Even it doesn't mean the floor doesn't exist. So there is a 5G, and if you want to put 5G, you can. I don't bother. 6S, 6P, 6D. There is a 6F and a 6G and a 6H. We never find electrons in them, so I don't bother writing them out. If you want to put them in, you can do it. Okay, it doesn't hurt us. And then the 7S and the 7P, and I stop right there. Again, you want to continue on, you can, but you don't need to. Here's why it's called the diagonal rule. Once we've done this, if we've done it nice and neat, you can do this part fairly quickly. We now are going to draw diagonals. So we just do it just like this. And if we've gone and taken our time to be neat, we can do this fairly quickly. And the way it works is like chutes and ladders. You're all familiar with the game, right? Okay, it's sort of similar in this way. If you start up at the top and slide down this ladder, this chute, and then go up to the next one and slide down it, you keep going down. When you get to the end, you go up to the next one and keep sliding down. The way it works is this. If you want to know which sublevel is lower in energy and therefore overall closer to the nucleus, it's the first one you hit. So the one that's closest to the nucleus, lowest energy, well, the first one we hit is the 1s. What's next? Well, the second most lowest in energy, closest to the nucleus, would be the 2s. Then the 2p. Then the 3s. Then the 3p. And there's the 4s. There's that overlap I was talking about. Then the 4s. Then the 3d. Then the 4p, the 5s, the 4d, the 5p, the 6s, the 4f, the 5d, the 6p, the 7s, and so on. Yep.
So does the 4s fill before the 3d?
The 4s will completely fill before the 3d, yes. And that takes us to the next part, which is how do the electrons go into an atom? Well, there's some rules that govern it. If you flip over to page 15, you see where it says representations of electron structure. You guys see that? You may put an X through the rest of that part of the page. Okay? Where it says representation of electron structure, you can put an X through that. So I'm talking about right here, guys. You don't have to worry about this. You don't have to worry about the top of the portion on the top. So let's take a look at it. First one up, the off-bound principle. The off-bound principle says that electrons first occupy the lowest energy orbitals available. Well, does that make sense? It should. If they go into the lowest energy orbitals available, that means it's a lower energy state, and we've already said there's a natural tendency in our universe to achieve a more stable state. That means the lower energy state, which means that the first electrons are going to go into the 1s. Now, we know that they can be anywhere in this region, guys. I'm just going to draw them right here. So there's one, and there's another one. So the first electron will go in. The second electron is going to go in there. Can I put the third electron there? No, because an orbital can only handle 2 electrons. So this is now filled. So what's next? What's the next best place to put them? The 2s. So I'm going to put the next one right here. Notice that this is a 2p, but 2s is lower in energy. So I'm going to put the next one there, and then I'm going to put the next one where? The 2s. And where am I going to put the next one? The 2s is filled now. Okay, the 2s only has one orbital, and that orbital is completely filled. So now, after 2s fills, now the 2p. Now watch though. The 2p, I can put it in any one of these orbitals. They're all equal in energy. I'm going to, by convention, put it into the m sub l value equaling -1. So the first one's going to go right here. Where should I put the next one? Well, those of you who live at home with siblings, maybe you know this firsthand. Unfortunately, maybe you don't. But I can tell you this, as much as my sisters loved each other, they were much better when they had their own room. Okay? There's a certain amount of friction that develops. Okay? If you have electrons, sure, all those orbitals in the 2p are equal in energy, but you can minimize the repulsion that naturally exists between electrons if you put them in their own room first. That's the whole reason behind Hund's rule. Page 15, Hund's rule states that degenerate orbitals will each receive a single electron before pairing begins. Okay, by pairing, we mean a pair of electrons means electrons. Anytime you hear the expression paired electrons, we mean electrons belonging to the same orbital. So that means that the first one, the next one's gonna go here, and then and only then will I begin pairing up before I move on. And finally, the Pauli exclusion principle basically states that no two electrons in the same atom in the ground state will have the same four set of quantum numbers. So that means that they could be in the same energy level, the same sublevel, the same orbital, but they'll have opposite what? Spins. So that fourth quantum number will be different. By the way, turn back to page 14. It's time to redefine ground state. So from here on out, when I ask you for the definition of ground state, this is what I'm going to ask you for. Ground state is now defined as this. Ground state is when all the electrons of an atom, are in the lowest energy orbitals available. Okay? Remember before, some of the electrons on lowest energy level. No, not anymore. Now ground state is when the electrons are in the lowest energy orbitals available and all paired electrons have opposite spins. Again, by paired electrons, we mean electrons belonging to the same orbital. So ground state again, when all the electrons of an atom are in the lowest energy orbitals available and all paired electrons have opposite spins. Guys, this model of the atom is just a wonder to behold. It's complex and as weird as it looks. It seems to be or standing up to the test of time, at least so far. Again, you won't. I'm not going to bet my life on the darn thing. I've seen us get, turned around thinking we had an answer for a good number of years, only to find out was the case. But this still explained line spectra. Remember how Bohr explained line spectra? Said line spectra was the result of the electron absorbing or emitting specific photons to undergo electron transitions. Each photon has associated with a particular frequency, which corresponds to a line spectrum. Okay, that explanation is exactly the same explanation as before, with one difference. In Bohr's model, an electron transition is when the electron would jump from one energy level to another. Now, Julia, electron transition is when it jumps from what? Orbital. From one orbital to another energy orbital. So, in order to jump from, let's say, the 2p sub z up to the 4s, it's going to require a certain amount of energy. That's going to have a photon. That's going to line up with a particular frequency, which corresponds to a line spectrum. So we explained line spectrum the same way as we did before. Still the result of the electron absorbing and emitting photons undergo electron transitions, but now electron transition refers to the electron jumping from one energy orbital to another energy orbital. Questions? Okay, at the top of page 14 are a couple of terms I just want to make sure that you're familiar with. Diamagnetism and paramagnetism. This will become more important as we go along into bonding. Diamagnetism and paramagnetism, guys, are not what you think of when you think of magnetism. When you think of magnetism, you're thinking of what is known as ferromagnetism. Ferromagnetism, ferro, F-E-R-R-O, what suggests what element? There's actually only three elements, common elements, that are ferromagnetic. Okay, or ones that you think of being able to pick up. Iron, cobalt, and nickel. Okay, a magnet will affect them. Aluminum, zinc, magnets don't affect them. Dimagnetism, paramagnetism is a different form of magnetism. It's much weaker. You'll look at it, it says dimagnetism is the property of weak repulsion to a magnetic field arising from the absence of unpaired electrons, while paramagnetism is the property of weak attraction to a magnetic field arising from the presence of unpaired electrons. You need to know which is which. You've got to keep these definitions straight. So that means you have to come up with some sort of mnemonic device that will sort of help you. Now, you might be wondering to yourself, when they say under diamagnetism, it's the absence of unpaired electrons, what that really means is that all the electrons are what? No. If there's an absence of unpaired electrons, that would suggest that all the electrons are paired. Okay? So why did they just say that? Well, it has to do with the way this was discovered and how they defined it. Let me explain what that means. If it were paramagnetic, okay, I could have a test tube full of that element, and if I tied it to a piece of string and I brought it into the place and brought it in close toward where, let's say I brought the string tied to the test tube into the place of a magnetic field, if the test tube moved toward the magnetic field, that would be a weak attraction. That would be paramagnetic. If I saw it sort of moving away from the magnetic field, that would be a weak repulsion. That's diamagnetic. You guys with me? I personally, to figure out a way to remember what